So in this problem, so they are asking us to find CLCD for the flat plate. So already we found the forces acting on the flat plate. What is the formula? What is the R dash formula? We discussed. Here we have P1. Here it is P3. Here it is P2. Chord length is C.
So P3 minus P2 into C.
So just pressure into area. Here it is the pressure difference. So P3 minus P2 into area is chord length. It is 2D, so it is simply C. That's why here I mentioned R dash or something. Okay, this is R dash. Once we know resultant force, we can find lift and drag. What is lift and drag?
So R dash cos alpha.
R dash cos alpha is lift.
R dash sin alpha.
R dash sin alpha is the drag. Okay, very good. And okay, if you write it in terms of pressure, it will be P3 minus P2C cos alpha. This is P3 minus P2C sin alpha. Okay, but here they are asking CL and CD. How to find it? Lift and drag, directly we have the equation. How to find CL, CD? This formula you are telling.
Yes, sir.
So half rho V square. Here the area is C into CL.
Yes, sir.
This is 2D, so it is L dash, and here you are using small l. Okay, but how to find this density velocity? Okay, this formula is correct, but we need this density and velocity. Okay, then to find the velocity, again we need the temperature. So if you want to apply this formula, then you have to assume what is P1, T1, rho, etc. and all. But it is not given here. Okay, if it is given, then using this direct formula, you can find this. What did I say? Okay, so if you know all this pressure, temperature, density, then you can use this formula. It will be very simple, like a 6-mark problem. Okay, but here it is not given. So we have two options to find this CL and CD. One is you have to assume, you can assume the flat plate is at sea level condition. You can take pressure is 1 atm, temperature is 300 Kelvin or 288 Kelvin, density is 1.225 calorimeter cube. Like that, you can assume first step, so that you will get all the P1, T1, rho 1. You can substitute here. This is the first method. This survey you used to solve if some values are missing, right? You will assume it. So one way is assuming the standard sea level conditions. And another procedure, second procedure, take the pressure ratios. The same formula I can write in terms of pressure ratio. So this is how I converted. So this is the normal formula. See, initially it is in terms of P2 and P3. Without this P1, we cannot find this P2, P3. So one way you can assume P1. For example, if you take across this oblique shock wave, from M1 you will find Mn1, then Mn2, then you will find P2 by P1 ratio. If you know the P1 value, you can directly find P2 and substitute here. Okay, this is the first way. Or another procedure, straight away we can use this pressure ratio instead of substituting this P1. For that, we are using this second method. So I am taking instead of S, C, and this half rho V square dynamic pressure, I am multiplying by gamma P by gamma P. So we know what is this gamma P by rho. It is A square. Okay. This gamma P by rho is the A square. Now I have gamma P1 V square divided by 2A square. You know V by A is M square. Now this will be the final term. So this half rho V square, we converted like this in terms of pressure and Mach number. Is that clear? This step?
Yes, sir.
Okay, now you can substitute here. So this will be the final CL in terms of only pressure and Mach number. I know what is L dash. It is 2 P3 minus P2 C cos alpha. C get cancelled. So remaining 2 cos alpha divided by gamma m1 square. 2 cos alpha divided by gamma m1 square. And remaining term, actually it will be P3 minus P2 by P1. This I can write it as P3 by P1 minus P2 by P1. Is that clear? So CC get cancelled. If you take 2 cos alpha divided by gamma m1 square outside, remaining will be P3 minus P2 by P1. That I can write it as P3 by P1 minus P2 by P1. So this is for CL. Then CD, simply instead of cos alpha, we have to put sin alpha. That's it. So this is the second procedure. So first procedure, you can assume P1, T1, rho 1. Second procedure, you can follow this formula. It's up to you. So for both procedures, you will get full mark. If you feel that remembering this formula will be difficult, straight away you can assume C level condition P1, T1, rho 1. No issues. Okay. So this is the final formula. CLCD formula. So we know M1, it is given 2.6, and they mentioned we have to find CLCD for 3 different angle of attack, alpha 5 degree, 15 degree, 30 degree. So alpha is known. These are all constant to gamma. Simply you have to find these two pressure ratio, P3 by P1, P2 by P1. This pressure ratio you have to find it. You know how to find this pressure ratio. For example, first I am taking that oblique shock wave, the bottom surface. This is station 1, 2, 3. Okay, so we know the Mach number. Theta is given, that is alpha. Once you know Mach number and theta, using the graph, you can find the beta. Okay, once you know the Mach number and theta, you can find Mn1. Once you know Mn1, you can go to the normal shock table. You can find this pressure ratio directly. So we found P3 by P1. Okay, now we have to find this P2 by P1. That is the upper surface we have to find 1 and 2. So this is the expansion fan. You know what is the procedure? First, from M1, you have to find gamma M1 using the graph. Then we know gamma, and also we know the theta. It is 5 degree. Okay, this is theta. This is gamma 1. From that we are finding gamma 2. From that we can find the M2. Then we have to use the isentropic table. From M1, using isentropic table, we are finding P01 by P1. Then from M2, using same isentropic table, we can find P02 by P2. We know the condition across the expansion fan. P0 is constant. So from these two ratio, I can find P2 by P1. Okay, simply P01 by P1 divided by P02 by P2 will give you P2 by P1. So I substituted here P3 by P1, and this is P2 by P1. This is Mach number, and alpha is 5 degree. Is that clear? And this is for 15 degree, same procedure. Okay, only theta is varied in both the cases. Then for 30 degree, same procedure. Instead of 5 degree, I used 30 degree everywhere. Same Mach number. You can see how the CLCD varies. For 5 degree, CL is 0.1, CD is 0.01. For 15 degree, 0.45, 0.12. For 30, 1.19, 0.6. Like that, CL and CD is increasing. Okay, next they are given CLCD for the diamond shape aerofoil. So theta they mention it is 10 degree, alpha is 15 degree. So look at this alpha and theta. Now we have to tell what are all the wave type we will get it here, 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 etc. What about the first point? What type of wave will get it? Alpha is 15, theta is 10. Or wherever you remember, first tell that corner. Always here it is oblique shock. Always here it is expansion. These two corners, and these two corners it is not required for us. Okay, these two corners. So this is oblique, and here expansion. Only this will vary depends upon the alpha theta ratio. Greater than means expansion, equal means no shock, less than mean oblique shock. Okay. So here it will be expansion. Actually, if you draw here also, then it will be like this mirror image. Oblique, oblique, expansion and expansion. This will be the difference in alpha and theta. What is the difference?
5 degrees.
5 degrees.
5, sir.
Okay, 5 degree, and here it will
5
be addition, sum of alpha and theta, that is 25. And behind the expansion,
20,
20. Always 2 theta.
20.
20. Okay. So this is the final diagram. Expansion, 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 and oblique. This is not required actually. And see flow turning angle in the above is 5, and in the below the surface it is 25, and here behind that expansion it is 20. Here's everything we found, and we are going for the what is it, final force calculation. So M1 is 3. So here, so you know this how pressure will act. This we discussed in the last class itself, which will be perpendicular to the this wall. Okay, and in this direction, resultant force will act. That only will resolve into lift and drag. Okay, and this will be alpha. Is that clear? So here also first we are finding resultant force in terms of pressure. From there we can find lift and drag. And already I explained how to resolve this pressure and pressure components. So last time we have taken diamond shape aerofoil at 0 degree angle of attack. So we resolved all the pressure component in the drag direction because lift is 0. But this is at angle of attack. So you have to resolve all the pressure component in the R direction. Once you know the R, then lift and drag you can easily write it. R dash cos alpha, R dash sin alpha. Okay. So I already told you for flat plate and diamond shape aerofoil, the resultant force will act in the midpoint and it will be normal to the chord line. Okay. And that resultant force only are resolving into lift and drag. So R will be simply the pressure difference, and L will be R dash cos alpha, D will be R dash sin alpha. So this basically discussed. Always will be 90 degree to the chord line. It will be located in the mid. So here it will be here, the midpoint resultant force. So I have to find the resultant force so that I can find L dash D dash, then CLCD. And so this is the reference line for the resultant force direction. Actually pressure will act normal to the surface. So it will be like this. So P2, P3, P4, P5, either it is acting. And normal sign conversion, positive, positive, negative, negative I'm taking. So I have to find this R dash. And I know this angle is theta, then everywhere it will be theta, this inclination. So then R dash means I have to resolve all this pressure component in this reference vertical line. So here if I resolve, I will get minus P2 cos theta into L. This is the force component acting here. And here it will be minus P3 cos theta into L. Then downward, it will be pointing upward. So it is positive P4 cos theta into L. Here also it is positive P5 cos theta into L. If you take this cos theta L outside, remaining you will get Okay, P5 plus P4 minus P3 minus P2 L cos theta. This is the formula. Then I can write L dash. Okay, same term. Into cos alpha, right? Then D dash, that is R dash sin alpha, R dash I know the pressure component, L cos theta into sin alpha. Is that clear? These two formulas.
Yes.
Yes.
Up to this, no doubt, right?
No, sir.
Okay. So again, to find the R dash, I need all these P2, P3, P4, P5 component and all, but I don't know what is P1, T1, rho 1, etc. So first step, if you want, you can assume this all P1, T1, rho 1. Straight away, using that, you can find all the P2, P3, P4. You can substitute here. Okay, you can proceed. And another option, we can go for the pressure ratios. So CL just now we derived 2L dash divided by gamma P1 square M1 square C. Similarly, CD will be 2T dash divided by gamma P1 Mn square C. Okay, so this I can write it as 2 divided by gamma Mn square C divided by L dash by P1. This I can write it as the same way I can write it 2 divided by gamma M square C into D dash by P1. So what I'm going to do, I'm going to divide this by P1 on both sides. Okay. So this is my final resultant force equation in terms of ratio. Sorry, here L cos theta. So once I know this, I can find D L dash, which is R dash cos alpha. But actually I have R dash by P1. So divide by P1 on both sides. That's it. Once you find this, substitute here, you can find L dash by P1. Substitute here, you can find CL. Same way you can do it for CD. Is that clear? This is the initial R dash. I have converted that in terms of pressure. This is my final equation. Okay. And L dash D dash also I converted into L dash by P1, D dash by P1. So that straight away I can substitute in this equation. L dash by P1, D dash by P1. Okay. So this is the general one. Just I have taken L dash and P1 outside. And the remaining procedure, you know. So first step is to find this R dash by P1. Okay. For that you have to find all these 4 pressure ratios. That's it. Once you found, you can substitute from first here, then L dash by P1, D dash by P1, then CL and CD. Is that clear? And you know, across this is station 1, 2, 3, 4, 5, right? So across the station 1 and 2, P naught is constant. Across station 2 and 3 also P naught is constant. Is that correct?
Yes.
And across this oblique shock, P naught is
Not constant.
not constant. And here it is constant. So this is the general condition. With that, we have to find all this ratio, P2 by P1, P3 by P1, then P4 by P1, then P5 by P1. All that ratio, we have to find it. First, they are finding P2 by P1. So we know the M1 using Prandtl-Meyer function. They are finding the gamma 1. Then using this formula, they are finding gamma 2. Then again using the table, we can find M2. With this procedure, last class itself we explained. Okay, so here we found P2 by P1. Then Across this, we know M2, I can find gamma 2, but it is same only. Then I can find gamma 3 using this formula. Now see the theta is 20 degree. Okay, and here if you take this will be a 5 degree. Okay, alpha minus theta, it is 5 degree. That only we have taken here. 49.76 plus 5, it is 54. Okay, now this theta you have to take it. You can find gamma 3 from that M3. Once you know M2 and M3, you can go to the isentropic table because this is the expansion fan, flow is isentropic. From M1 you can find P0 by P1, M2, P02 by P2, M3, P03 by P3. So what we need is P2 by P1, P3 by P1. Simply the ratio of this stagnation to static pressure ratios. Okay, we got two value. Then we have to find it for the lower surface. Is that clear? This slide, any doubt?
No, sir.
So in the lower surface, we have the oblique shock. We know how to find it. We know M1 and theta. See here, theta is 25, alpha plus theta. This theta we are taking. For that, we are finding beta. Then we can find Mn1. Then go to the normal shock table. We can find all these ratios. P by P4 by P1, T4 by T1, P04 by P01, Mn4, everything you can find it. Once you know Mn4, we can find M4. Here also the theta should be 25. Then after that, so directly we can find it. Okay, from the table itself, we found the P4 by P1. Now we have to find P5 by P1. Okay, so I know M4. From that, I can proceed for this expansion fan. From M4, I am finding gamma 4. Then here theta I used to 20. Okay, theta is 20. You see that I can find gamma 5. See 18 plus 20, it is 38. From there I can find Mach number 5. So again, if this is expansion fan. So for M4 I am finding stagnation to static pressure ratio. M5 I am finding the static to stagnation pressure ratio. If you divide these two, you will get P5 by P4. Already I know the P4 by P1. Now using these two, I can find P5 by P1, like P5 by P4 into P4 by P1. Now I found all four pressure ratios. Simply substitute here. You will get R dash by P1, then L dash by P1. But we have that term L. Finally, we are going to find that also. Okay. And if you substitute that L dash by P1, you will get this term. 2 value we know, gamma is 1.4, M is, what is the value? So M is 3, Mach number is 3, chord we don't know, and this term has the L, so finally we have the L by C term. Okay, we don't know the dimension of the aerofoil, so we have L and C term in the CL. Similarly, CD also there will be L and C term. Now we are going to find that L and C also. So this is the diamond shaped aerofoil. Thickness theta L. So they are finding cos theta. So here we have taken theta is 10 degree. So cos theta is equal to, so C by 2 divided by L. The total length is C. So cos theta is C by 2 divided by L. From there I can find the L by C, this value. Is that clear? So here 10 degree, this length is L, overall chord is C, so half value is C by 2 for this right angle triangle. Okay, here we have T by 2. So for this right angle triangle, they are finding cos theta, it will be C by 2 by L. Rearrange, you will get L by C is this value. Now you can substitute this in this L by C, you will get CL is 0.42, CD is 0.12. So next problem. So this is the expansion fan. They're asking us to find maximum deflection angle, and they are telling free stream Mach number is 1. We have to find the maximum deflection angle. I will proceed. Maximum means this can be deflected to 90 degree, even more than 90, 180 and all. But how to find that maximum theta? Actually, there is no much clarity, right? They didn't give much information. So how they have taken? So if theta increases, Mach number, that is M2 also will increase, right? Okay, this deflection increases means Mach number also will increase. So they have given maximum deflection angle. Instead, they are proceeding with the Mach number. They have taken maximum Mach number. What would be the maximum Mach number theoretically? So we are assuming the Mach number goes to infinity. Okay. For that, we are going to find corresponding theta. That should be the theta max. Okay. Then how will you proceed? You know M1, it is 1. You know M2, it is infinity. You have to find the theta. What is the procedure? You can find gamma M1 and gamma M2. What is gamma M1 value?
125.
So 125 page number gas table you can check. For every Mach number you can find gamma M, which is given like omega M. So for M1 is equal to 1, gamma M1 is 0. Then gamma M2, what is the maximum Mach number they are given in the gas table in this page number 125? Okay,
So,
maximum they are given for.
129. So 5 only we have got.
Okay, maximum they used to give up to Mach number 5. Okay. Then if it is not there, we have to go for this formula. Okay. Substitute M2 is equal to infinity and tell the value. For example, if I put infinity here, the whole term will be infinity. If I put infinity here, again the whole term will be infinity. Then it can be like root of gamma plus 1 divided by gamma minus 1. Tan inverse of infinity minus tan inverse of infinity. Is that correct? So I am finding Mach number, maximum Mach number. From there I am going to find theta max. For M1, I found gamma 1, it is 0. For M2 is equal to infinity, there is no value in the gas table, so we are going for this formula. Okay, so here I am substituting infinity, here I am substituting infinity. Tan inverse of infinity is pi by 2. Now if you solve, you will get gamma 2 will be 130.45 degree. Okay, so this is 0, this is 130.45 degree. Then theta also the same, 130.45 degree. Right? Okay. So here we are comparing the drag of two objects. One is cylinder with a dia D and diamond shaped aerofoil with a theta of 5 degree. Here also the thickness is equal to dia. Okay, the thickness is equal to dia. We know the free stream Mach number 5. It is same for both model. And additionally, they have given CD of this cylinder, which is 4 by 3. So two objects we are going to compare how the drag varies. So first is cylinder with a CD value 4 by 3. Second one is diamond shaped aerofoil. Thickness is the D, theta is 5 degree. And you know the drag value of this diamond shaped aerofoil, what is that? The derivation we found it, right? Station
Yes, sir.
1, 2, 3. What is the formula?
P2 minus P3 into T, sir.
P2 minus P3 into
T.
Okay, T instead of T, they are telling D. Okay. Okay, thickness is D, so I am taking D. Good. Then here they mention CD. Then which formula you can take it? And normal formula. Okay. Okay, instead of CD, I can write 4 by 3. And I don't know rho V. We know how to convert this half rho V square in terms of pressure and Mach number. How to convert? Okay, now we can, they're asking us to compare. So we can find the ratio of these two drag so that you can easily compare it. I'm taking D diamond divided by D cylinder. So I'm getting P2 minus P3 into D divided by these two. I can take it here. So the remaining will be gamma P1 M1 square D 4 by 3. Okay, DD get cancelled. This 4 by 3 and this also get cancelled. So remaining I can write it as 1 divided by, okay, 3 divided by 2 gamma M1 square P2 by P1 minus P3 by P1. Is that correct? So I have taken diamond first, cylinder second, and numerator denominator. Here it is just inverse. Cylinder divided by diamond shape aerofoil. This is easy. Okay, the formula. Okay, so this formula already we know that. Here we are taking general drag equation, substitute CD, then area. Instead of half rho v squared, you substitute gamma p m squared by 2. Then we will simplify it like this: 3 divided by 2 gamma m1 square p2 by p1 minus p3 by p1. So to find this drag ratio, we know the Mach number 5. We know the gamma of air, it is 1.4. Simply have to find P2 by P1, P3 by P1 from this diamond shape aerofoil. Okay. So that to find the P2 by P1, P3 by P1, you know the procedure. So this is oblique shock. First you have to find the Mn1. Okay. So using M1 and theta you can find beta. Then Mn1 you can find it. Then go to the normal shock table, you can find the Mn2, P2 by P1, etc. From Mn2 they are finding M2. Okay, and from the table itself we are getting P2 by P1. Then from M2 we can find gamma M2, then gamma M3. From that M3 we can find it. Then this is expansion, so P0 is constant. From M2 I can find the pressure ratio, M3 I can find pressure ratio. Then I have to find P3 by P1. So directly I cannot relate P3 by P1. So I am taking these two ratio. So this is already we found it here. And this one using isentropic table I am finding P02 by P2, P03 by P3. From this ratio I can find this. So P3 by P2 is equal to, I can write it like P3 by P03, P2 by P02. This equal, so you will get P3 by P2. Then substitute both the pressure ratio, Mach number, gamma value. Then compare, we are getting drag of the cylinder is around 18 times the drag of the aerofoil.